These case studies show how different companies turn AI ideas into real products, real workflows, and real business decisions. The useful part is not just what they built, but the patterns behind why each approach fits a different problem. Palantir is often used as the reference point for a very specific startup shape. A company that begins with a hard technical product, a small set of demanding customers, and a long path from service-heavy work to scalable software. That template matters because it explains both the strengths and the tensions in the business model. The origin of the forward-deployed engineer becomes clearest through Palantir, a company that turned close customer work into a repeatable business model. The point here is to separate the myth from the mechanism and see how field deployment became part of the product itself. The evidence comes from public materials and reporting, not legend. Palantir matters because it made a pattern visible early, a technical specialist embedded with a customer, learning the customer's problem first, then shaping software around what actually gets used. Enterprise software can look excellent in a polished demo and still collapse once it meets real data, real users, and real operational constraints. That gap is where many products stall because the customer's workflow is already messy and no one wants a brittle system in the middle of a critical process. Palantir attacked that gap by putting technical teams into the customer environment instead of waiting for adoption to happen on its own. In that model, the deployment work is not an add-on after product design. It is how the product gets discovered in the first place. That is a bottom-up path to product development. Each engagement starts with one specific problem, then produces a working solution, and over time reveals what can be repeated and hardened into a broader offering. The field becomes the laboratory, and the product grows out of what proves useful there. A field engagement starts by mapping the real workflow, who decides where the data comes from and which step is slow or broken. From there, the engineer builds the smallest useful version, tests it with the people who will rely on it, and keeps iterating until the system changes the actual outcome. Two cultural details make the operating style easier to see. They look informal on the surface, but both point to a company that treated field learning as something that had to be organized, shared, and refined. Hobbikin shows that the company built recurring internal rituals around deployment and product learning. Teams working in the field need a way to turn scattered observations into shared practice, and events like this help synchronize people who are solving hard customer problems in different places. That phrase captures the judgment call in fieldwork. The team needs a strong hypothesis to move quickly, but it also has to stay flexible enough to change course when the customer environment proves the first idea wrong. Those details make the core ideas behind the role concrete. Now the lesson can be stated plainly. The FD exists because some customers need someone who can understand the product and shape the deployment at the same time. The role emerged because complex customers needed people who could both understand the product deeply and adapt it to the deployment on the ground. That combination is what turns a general technical skill into a customer-facing operating role. Mission-type tactics mean the field team is trusted to solve the customer's immediate objective without waiting for a perfect central plan. Local judgment matters because the situation on site changes faster than a distant product process usually can. Field autonomy gives the engineer enough independence to decide in real time. If every answer has to come from far away, the deployment slows down and the moment to earn trust can pass. The first task is not to pitch the product, but to understand the customer's operational pain. Once that pain is identified clearly, the team can build something that fits the real job instead of an imagined one. The engagement moves through a life cycle. Learn the problem, build a prototype, and then harden it until it works in production or near production use. Each stage gives feedback that shapes the next version. The real test is speed to meaningful value. If the customer does not feel a noticeable improvement early, the deployment risks becoming another stalled pilot instead of a tool people actually adopt. Building a demo is the easy part. Hardening it for real use is where the work gets serious. The system has to survive messy data, changing users, and the pressure of daily operations before it counts as deployed. Once the workflow stabilizes, the team has to separate one-off custom work from repeatable capability. Good handoff discipline keeps the customer supported while also turning the lesson into something the company can reuse. The comparison makes the shift easy to see. Before the FD, the problem often sits in a pilot that never becomes real usage. After the FD, the work is aimed at narrowing the problem, shipping something usable, and feeding concrete lessons back into the company. A table works well here because the difference shows up at every stage of the engagement. The frame changes from broad and vendor-led to specific customer-led and tied to actual workflow outcomes. Each row shows the same transition from distance to closeness. The important change is not only technical quality, it is whether the system gets pulled into everyday work and whether the company learns something precise enough to improve the next deployment. That table leads to the business point. The FD is not just a technical fixer. The role exists to turn capability into adoption, because in enterprise software and enterprise AI, value only appears when people actually use the system in their environment. Palantir also helped normalize the career path. For engineers, the appeal is a role that stays technical, stays close to customers, and still gives enough ownership to shape what gets shipped, especially when the deployment is too complex for a generic platform alone. The broader lesson is about how the role comes into being. Field deployments create the first proof that a solution matters. That proof supports productization, and productization makes the work repeatable enough for the role to scale beyond one customer at a time. That sets up the next problem. A modern AI company may want the same field-driven function, but it has to build it deliberately rather than inheriting it from older enterprise habits. The question becomes what parts of the Palantir pattern still hold, and what has to change. This part traces a concrete organizational shift. How OpenAI moved from a general solutions architecture posture to a dedicated forward deployed engineer function, and why that mattered in practice. A case like this matters because it ties structure to field impact. Instead of treating the org chart as abstract theory, the reporting lets you see what changed once the team was set up a certain way and why interviews make that change visible. The pattern starts with a problem that no single team can own cleanly. It is too messy for product alone, too technical for account management, and too important to handle as ad hoc support. A dedicated FD sits inside the product organization, but it works close to the customer, close to the lab, and with enough autonomy to adapt quickly. The point here is to separate a narrow support role from a broader engineering role. That matters because the title alone can hide very different expectations for how work actually gets done. A solutions architect usually helps turn a product into something a customer can adopt safely. The work leans toward explanation, scoping, and catching bad assumptions before launch, so the emphasis is on design clarity rather than hands-on delivery. A forward-deployed engineer sits closer to the problem itself. That person is expected to shape the solution, build or adapt it, get it running in production, and then use real usage data to refine it. So the role covers the whole path from first conversation to working system. That difference shows up sharply in AI, because a demo can look finished long before the system survives real use. Messy data, fragmented workflows, low tolerance for errors, and deployment constraints all turn a promising model into a fragile product, and the FD role exists to deal with that gap. Growth at that scale signals that the work has crossed from occasional help into a real operating function. The headcount matters less than the pattern underneath it. Repeated customer pain, repeated solutions, and enough demand to justify dedicated people. A small team can handle one-off requests, but repeated pain changes the shape of the job. Once the same kind of problem keeps appearing, the organization stops treating it as a favor and starts treating it as a function with ownership, process, and staffing. That split keeps the roles from blurring together. One person frames the solution and aligns the stakeholders. The other gets into the customer environment and makes the design survive real conditions. The architect side is about translating needs into a workable plan, while the field engineer side is about turning that plan into something that actually runs. The risks are different too. One can stay too abstract, and the other can become trapped in custom work that never improves the broader product. That custom home image captures the difference well. The design can be clean, but the site always introduces friction. Slope ground, changing requirements, and unexpected constraints force adjustments, and AI deployments behave the same way when the real environment starts pushing back on the plan. That comparison shows the real job of the FD, turning a promising prototype into something people actually use while sending practical lessons back to the lab. Those four questions keep the discussion grounded. They separate surface-level success from the actual changes in workflow, usage, and product understanding. The first question identifies the pain point before anyone intervened. The next two track whether the fix reached real production use, and the last one makes sure the field work improves the product, not just the single customer deployment. That gap is common. A demo can impress a small pilot group, while the daily workflow still fails. The effective fix usually changes the surrounding system too, not just the model itself. Less manual work, better retrieval from customer data, clearer guardrails, and a cleaner handoff between people and the model. Once the deployment starts fitting the real task, usage can spread beyond the sandbox and into production. At the same time, the lab gets evidence about which prompts, retrieval choices, approval steps, and review patterns survive contact with real users. The title only makes sense once the practical work is visible. Customer discovery, system design, evaluation, and governance all sit inside the role. That mix is what turns the job from a label into real engineering practice. An FD is constantly translating between three pressures at once. Product cares about value, engineering cares about feasibility, and the customer cares about whether the system actually helps in their workflow. The first job is to understand the real problem before any model work starts. If the problem is unclear, every later decision becomes guesswork. That means tracing the workflow end to end, what people are trying to accomplish, where handoffs slow things down, and who has to sign off before something can move forward. In AI settings, the same conversation also has to cover what the model must never do, where a human has to step in, and which outputs are only safe as drafts. Once the problem is understood, the engineer needs room to act close to the customer. That kind of local decision-making keeps the work moving without waiting for every choice to climb a long approval chain. The idea is disciplined autonomy, not freelancing. The person nearest the problem can adjust rollout order, interface details, evaluation design, and workflow changes because the pace of the field is faster than centralized review can handle. Once autonomy is in place, the next question is how the model fits into the full service. A language model on its own is not the product. The architecture around it is what makes it usable. That architecture usually combines the model with retrieval, prompt design, routing logic, logging, human review, and feedback loops. The goal is a system that is reliable and understandable because a good FD treats the model as one component inside a maintainable service, not as a magic answer box. At deployment time, the main design problem becomes the handoff between person and model. The best workflow depends on which side should draft, decide, review, or escalate at each step. Sometimes the model writes a draft and the human approves it. Sometimes the human provides context and the model speeds up synthesis. And sometimes the model handles routine cases while the human takes the exceptions. The system works only when those roles match the real job instead of an idealized user story. Once the workflow exists, the system has to earn trust through testing. Deployment should follow evidence, not optimism. Evaluation means checking the system on representative tasks before launch and after each change. If the team can measure success, catch regressions, and decide on expansion from that evidence, the product behaves like an engineered system instead of a demo held together by enthusiasm. The last piece is what happens when the system can take actions on a user's behalf. Capability alone is not enough. The system also has to stay inside safe boundaries. Reliability asks whether the agent does the right thing again and again. Governance asks what rules, controls, and review steps keep it from crossing the line, because a system that is clever but unsafe is not ready for broad use. OpenAI's FD role now covers the full path from first discovery to post-launch feedback. The important shift is that the job is not just support at the edges. It helps turn a model into something a customer can actually rely on. That sequence shows the role as a lifecycle function. The FD starts by understanding the customer problem, then narrows the scope, shapes the system, helps launch it, supports real usage, and feeds results back into evaluation and product changes. A clean way to think about it is as a chain of decisions and outcomes. Each step answers a different question, from what the customer needs to whether the solution actually works in practice. Discovery means getting past the surface request and finding the actual task the customer is trying to complete. If that problem is framed poorly, everything that follows becomes harder to design well. Scoping is where judgment matters. Some ideas are technically possible but too risky, and some are good ideas that should be deferred until the system is ready. System design turns a useful idea into something that can survive real use. That means thinking about data flow, reliability, guardrails, and how the pieces fit together in production. Production rollout is the point where the work leaves the lab and enters the customer's world. Now the concern is not just correctness, but integration, stability, and operational fit. Adoption matters because a system that nobody uses does not create value. Helping people learn the workflow, trust it, and fit it into their habits is part of making the product real. Eval feedback closes the loop. The results tell you where the system is strong, where it breaks down, and what needs to be improved before the next release or the next customer. That is what separates the role from a simple pre-sales or post-sales function. The FD helps convert raw model capability into something repeatable, usable, and valuable over time. The market effect is real, but it should be kept in proportion. Once a major lab formalizes an FD organization, the role stops looking like a one-off quirk and starts looking like a legitimate path inside frontier AI companies. That visibility changes how people position themselves and how employers think about adjacent jobs. Candidates can point to a known role with a clear shape, and companies can start defining related positions around it instead of treating the work as an odd special case. The best candidates can connect technical design to what customers actually need, and they stay grounded in how software gets deployed in the real world. On the hiring side, the title matters less than whether the person can translate messy needs into implementation, make trade-offs under uncertainty, and feed product learning back without turning every account into custom engineering. That gap is the real reason the function exists. When a model or product is strong in the lab, but still hard to use in a customer setting, embedded fieldwork becomes the bridge that turns capability into something people can actually adopt. The next part makes that concrete by following the role into a real customer-facing deployment. That is where the abstractions turn into decisions, constraints, and the daily work of getting a model into use. This part traces how a field-facing role turns a voice model from a lab capability into something a real customer can use safely. The focus is the work between model potential and production reality. The setting matters because a call center is already full of live pressure, speed, noise, interruptions, and consequences. A voice model has to fit into that environment without slowing people down or creating new errors. That role becomes visible when the question stops being whether a model can impress and becomes whether it can hold up inside the customer's actual work. The engineer is there to bridge that gap. The sourcing note matters because it separates company claims from a realistic composite of how this work typically unfolds. That keeps the lesson grounded without pretending every detail comes from one fully verified deployment. The job starts with a specific operational problem, not a generic AI showcase. In voice work, that means finding the place where latency, guardrails, or handoffs would break the system if it were dropped in too casually. The first useful question is usually the messiest one. What is failing on the ground right now? By shadowing the workflow, the engineer can pick one narrow slice where the model can help without taking on the whole problem at once. That gap is where these roles exist. The lab may have a strong model, but the customer still has integration friction, latency constraints, weak processes, and edge cases that only show up when real people use the tool. The first phase is discovery, and it is much more concrete than a requirements meeting. The work is to learn the process as it actually runs, so the solution is shaped by reality instead of assumptions. Discovery means watching handoffs, noticing manual steps, and asking why each step still exists. Some steps are manual because they are risky, some because they are overlooked, and some because nobody has tried a better path yet. The engineer needs enough freedom to adjust the solution after seeing the live workflow. That autonomy lets the work respond to what the customer actually needs instead of waiting for a generic plan to be approved somewhere else. Most deployments do not fail in one dramatic moment. They fail through small mismatches. A prompt that works in clean tests but not in noise, a missing data field, a handoff nobody owns, or an interface that adds friction instead of removing it. Once the workflow is clear, the next move is to put the model inside it. The customer should not have to rebuild their process around the model. The model should fit the process they already rely on. Embedding can mean wiring the model into transcripts, customer records, routing logic, review tools, or the live agent console. The important thing is that it sits where the work already happens. At this point, the question becomes narrow. Where does it help first, and what path is safest for production? A prototype can be messy and temporary, but a production system has to be durable and reliable. Early value has to show up quickly enough to keep the customer committed. In a call center that might be less after-call work, faster responses, or cleaner summaries that save supervisors time. A simple process map makes the progression easier to hold in mind. It shows how the work moves from understanding the problem to learning from the live system. The point of the table is the sequence. First, the engineer learns the workflow, then builds a test around a real task, then adds evals, then rolls out carefully, and finally uses live failures to improve the product. Evaluation is where subjective confidence turns into a repeatable standard. Instead of asking whether the model feels good, the team asks whether it meets the customer's actual reliability needs. A lab test can measure general ability, but field evals have to measure whether the system is useful for one customer's job and safe enough for that environment. The target is not abstract intelligence. The target is a specific outcome under real constraints. For voice work, the tests usually revolve around understanding intent, handling interruptions, staying inside latency limits, avoiding unsafe outputs, and preserving the details that downstream teams need. Those are the things that make or break the experience. That is why the role is part engineering and part translation. The engineer sees the workflow, turns it into a test, and helps the customer decide what level of performance is actually acceptable. Evaluation cannot end at launch because the edge cases keep changing. As the customer uses the tool, the distribution shifts, and the team needs a live loop for catching new failures. The return path is what makes the role more than implementation. Field observations become product input, and the customer site becomes a source of learning for the broader team. The first deployment matters, but the real difference shows up when the lessons travel back upstream. That is what turns a one-off project into organizational learning. What comes back may be failure examples, workflow changes, annotation guidance, edge case transcripts, latency findings, or safety concerns. Those observations help the research and product teams see the system from the customer side. The discipline is to avoid trapping that knowledge inside a bespoke project. If one customer exposes a repeated weakness, the engineer helps turn it into a product requirement that can help many users. That feedback loop is why a frontier lab values the role so highly. The company is not only buying delivery, it is buying a way to learn from delivery and improve the core product. Production changes the meaning of failure. Before rollout, failure teaches. After rollout, failure affects real work and real users. That shift is why rollout has to be careful. Once the system touches live work, problems are no longer just technical findings. They become interruptions to the business. A safe first deployment is usually small on purpose. A narrow queue or a single group lets the team watch how the system behaves before exposing it more broadly. A tool can be live and still in use. The engineer watches whether agents keep it on, whether supervisors trust it, and whether the workflow is actually faster or easier. Before the field work, the customer has an idea and a model with general ability, but the constraints are still unresolved. Afterward, there is a bounded use case, a tested path, a live deployment, and a clearer next step for the product. A good field deployment can do more than solve one customer's problem. It can expose a feature or capability that belongs in the general product. The best field work often leaves behind a trace that other customers need too. What started as a one-off solution can become something the broader product should include. In a voice model, that might be a better conversation pattern, a safer control, or a cleaner integration point. Once that pattern proves useful in the field, it can move from custom work into the standard offering. That is the full origin story. The role exists because useful deployment requires technically deep customer-facing work that runs from discovery to evals to rollout to product learning. The thread has to stay intact from the first conversation to the last handoff. OpenAI's own framing makes the role look broader than support and narrower than general research. It covers the whole path from understanding the customer to shaping the system and feeding the result back into the product. Those job description terms map to the full life cycle of turning model capability into customer value. They describe a role that participates before, during, and after deployment. That shows how the field version of the job has matured. The engineer is expected to help define scope, shape the system, manage rollout, watch adoption, and carry lessons back to the team that can improve the product. For job seekers, the signal is clear. The role rewards people who can move across customer conversations, technical implementation, and product feedback without losing precision. The strongest candidates can hear the operational problem, build a workable path, and explain what should change upstream. One useful rule captures the whole story. This role exists where a good model only becomes valuable after it is embedded, tested, deployed carefully, and tied back to learning. That chain is the core pattern to remember. The model is not the endpoint. The workflow, the evals, the rollout, and the feedback loop are what turn capability into value. Once that chain makes sense, the natural comparison is with other organizations that solve the same problem under different labels and product philosophies. That comparison is where the next section begins. Anthropic uses a different label for a very similar kind of work, and that choice tells you something about how the company thinks about deployment, safety, and product integration. The role is not just about being close to a customer. It is about turning model capability into something a real organization can trust. The interesting question is not whether the work exists, but how the company frames it. A different title can change the expectations around the job, the kind of problems it solves, and the identity the organization wants to project. The underlying pattern still looks familiar. Take a model, fit it into a customer workflow, find the fragile pieces, and feed those lessons back into the product. What changes is the emphasis because some labs want the role to sound more like application engineering and less like a consulting-style field function. These four terms pin down the territory of the job. Enterprise deployment means putting the system into everyday organizational work. Workflow is the actual sequence of tasks people follow. Evaluation is how the system gets tested before shipping. And governance is the set of controls that keeps risk in bounds. That wording points to a different starting point. The goal is not only to embed engineers near a customer, but to make a strong model fit the standards of a serious environment, where trust, clarity, and operational fit matter as much as raw capability. That title carries a set of signals. It suggests a role that is closer to model behavior and safety, more oriented toward productized implementation, and focused on translating customer problems into engineering language. The first implication is alignment with how the model behaves and what safety standards it has to meet. In a lab setting, that matters because the role is often judged not just by usefulness, but by whether the system stays within acceptable boundaries. The second implication is that the work should feel like part of a product system, not a one-off service engagement. That changes the mindset. The engineer is building repeatable solutions, not just delivering a custom fix for one account. The third implication is translation. A customer may describe a pain point in business terms, but the engineer has to turn that into measurable requirements, failure modes, and system behavior that a technical team can actually act on. A rename can be cosmetic, but it can also be strategic. Companies use titles to signal whether the work belongs to services, product, research translation, or some mix of all three. And that signal shapes who owns the work, who gets credit, and who carries the responsibility. The work can stay familiar while the job title changes around it. What matters here is how the scope, constraints, and success criteria shift when a role is framed as applied AI engineer instead of traditional FD. The same technical core can sit inside a different operating model. One role may emphasize customer-specific delivery, while another emphasizes repeatable patterns and broader deployment across many environments. A traditional field-driven story usually begins with a very specific pain point already on the table. The engineer then learns the workflow, works within the customer's constraints, and shapes the system until it fits real daily use. That framing pushes the work one step earlier from one customer to a broader class of settings. The emphasis shifts toward reusable design, stronger evaluation, and guardrails that keep the system dependable when the environment changes. A side-by-side comparison makes the difference easier to see. Each row shows the same underlying goal, but with a broader engineering lens after field involvement. On the left, the problem is still vague and the workflow is messy. On the right, the use case is narrowed. The system is wrapped with supporting logic, and adoption becomes something you can measure instead of guess at. The feedback also becomes more concrete, because teams can point to specific failures and missing capabilities. That is the practical center of the role. Whatever the title, the engineer is still making the system work in a way people can rely on again and again. Applied AI work often looks like ordinary product work with a sharper edge. The function is still to solve a business problem, but now the cost of a wrong answer, a stale source, or a weak review step is much higher. A model can look impressive in a demo and still be unsafe for production. Support teams care about correctness, policy compliance, and account-specific context because one bad response can trigger escalations or create legal trouble. The useful move is to separate the business problem from the model itself. Once the task is decomposed, you can choose the right workflow instead of assuming raw model ability is enough. Those 5 pieces cover the whole job. Identify the costly tasks, design the right LLM system, decide how humans and the model share work, define measurable success, and set guardrails for uncertainty and risk. That is the difference between a clever prototype and a system an organization can trust. The real work is adaptation. The model matters, but the surrounding decisions determine whether the system fits the people, the policy, and the operational constraints of the company using it. Some labs avoid the label because it can imply the wrong job shape, the wrong priorities, or the wrong company culture. The title matters here because it signals how the work fits with product, research, and deployment. Those choices usually come from 3 places: how the role is framed, what the work actually contributes, and what the company wants the title to communicate outwardly. The label is doing more than naming a job. It is also shaping expectations. Some companies want the role to sound like deep application engineering rather than broad field support. That distinction matters when the work involves technical judgment and system-level understanding, not just customer-facing implementation. Another reason is that the role can feed directly into model improvement. The engineer is learning from real deployments, finding where the model succeeds or fails, and turning that evidence into better behavior in production. A third reason is cultural. A lab focused on safety, alignment, or careful release management may prefer language that sounds disciplined and engineering heavy because that better matches how it expects people to work. Job titles change quickly in this market, so the safest habit is to check current company sources before treating any label as fixed. When the naming matters, use the company's own materials as the claim and separate that from anything you have independently confirmed. Palantir is useful here because it shows the older, more explicit version of the same operating model. The point is to understand how close work with customers changes both the software and the way the team learns from deployment. Palantir's forward-deployed approach puts engineers close to the customer's actual environment, where the constraints are real and the workflow is messy. That matters because the software improves by being shaped around those conditions, and the lessons from each deployment can flow back in the product itself. Anthropic's framing keeps the same basic need for integration and trust, but the technical problems shift. When the core product is a general-purpose model, the work centers on hallucinations, instruction drift, tool use, and inconsistent behavior, so prompt design, retrieval, evals, and guardrails become the main levers. That comparison makes the role easier to name. Palantir represents field deployment around enterprise software, while Anthropic shows the same function recast for a frontier model. The underlying job is still to make the system work in the real world, but the methods now follow the behavior of the model itself. Origin stories do more than describe where a role came from. They reveal what the company thinks the role is for, and that changes how you read the title. A hiring story is really a theory of the business. If a company describes a role one way, it is also showing you how it sees itself, what it values, and where it thinks the hard work lives. For an FD, the emphasis lands on context. Capability by itself is not enough. It has to be brought into the customer's environment, with the right constraints and the right problem in front of it. Applied AI engineer language shifts the emphasis toward translation. The company is saying that raw model ability has to be made safe, understandable, and dependable before it can create customer value. Those two frames overlap, but they point the role in different directions. One stresses being close to the field. The other stresses disciplined application, and that distinction can shape whether the job feels like deployment, research translation, product integration, or all three. For a candidate, the market rewards evidence of end-to-end judgment. A strong story covers how a problem was found, how the system was designed, how it was evaluated, and what was learned once it ran in production. That matters for operators too, because the title itself does not make deployment happen. What matters is whether the person in that role is expected to cross the boundary from model capability into real organizational use. When a label changes, the safe move is to inspect the work, not the branding. Ask who owns discovery, integration, evals, deployment, and feedback to the model team, because the answer tells you how the company actually operates and sets up the fintech example that follows. Ramp shows how the forward-deployed engineer idea changes when the customer is a finance team with real controls, audits, and trust requirements. The focus here is not the title itself, but the operating model behind it. That frame matters because the work becomes legible only when you start from the problem the customer is trying to solve. Once you do that, the engineer's role stops looking abstract and starts looking like direct support for a specific workflow. That same standard keeps the chapter grounded. Ramp works well as a test case because it shows the FD pattern under real product pressure, where speed has to coexist with evidence, and where deployment details matter more than broad claims. In finance, a system can't just be useful on day one. It also has to stand up to internal review later. That changes the engineer's job, because every automation has to be judged not only by how much time it saves, but by whether it can survive scrutiny. The reporting points to a clustered structure rather than a scattered one. That setup suggests ownership. A small team can stay close to a customer problem, handle integrations, and keep responsibility for the outcome instead of handing pieces off across the company. That distinction is important because org charts can hide the real function of a team. A pod gives enough autonomy to move quickly, enough specialization to deal with technical edges, and enough customer proximity to see what actually fails in production. Palantir is the nearest comparison because the core logic is similar. Put technical people inside the customer environment so the platform can be translated into operational value. RAM's version is shaped by fintech, but the aim is the same. Get close enough to the workflow that the workflow itself can change. Fintech changes the FD role because the problem is rarely just a model call. It is usually a regulated workflow with real business risk. The important shift is from building a demo to shaping something that can operate safely inside a company's rules. A pod is the small team that can cover all the pieces at once: problem discovery, system integration, evaluation, and feedback into the product. That matters because enterprise work usually fails when those responsibilities are split too far apart. The last mile in fintech is often not a single feature request. It is the messy gap where policy rules, risk controls, and how people actually work all have to line up, and that is where simple AI demos usually break down. That is why the FD becomes an adapter rather than just a helper. The job is to take a general platform capability and shape it into something that fits one company's constraints, approvals, and operating habits. A comparison makes the change easier to see because it turns an abstract role into concrete differences in workflow, ownership, and success criteria. The table shows how the same AI idea becomes much more usable once the FD has done the adaptation work. The left side is what a raw request often looks like. People know the outcome they want, but not the safest path to get there. The right side is what changes after the FD work. The AI sits inside a real process with guardrails, review steps, logs, and feedback that can actually improve the product. That is the central idea to keep in mind. The FD is not just installing AI. The FD is making the workflow strong enough that AI can keep working when it meets real users, real controls, and real business pressure. This part is about how strong technical capability becomes a repeatable operating model. The important question is not whether the team can solve a customer problem once, but whether it can do it reliably across many customers. A company can build something impressive before it has the process to deploy it cleanly. That gap shows up when the product works, but the organization still struggles to turn it into a stable customer experience. Early on, engineers can sit close to customers and patch together custom fixes. Once demand grows, that approach becomes too expensive and too fragile, so the team has to turn those ad hoc efforts into a process that can scale. That is what the FD pod model tries to preserve and formalize. The team stays near the customer, but it also owns outcomes and feeds what it learns back into the product instead of leaving the work as a permanent custom service. The deeper point is organizational. The company is building a system that captures what the field learns and turns it into a repeatable asset, rather than depending on a few people improvising under pressure. That role matters most in a fintech scale-up, where the work sits between founder-style support and slow enterprise implementation. The customer needs real adaptation, but the company also needs a way to ship that adaptation without losing speed or control. Mission-type tactics mean giving a team a clear outcome and enough freedom to adapt the execution. In fintech, that matters because the product has to fit different customers, different controls, and different risk limits. The point is simple. Leadership sets the destination, but the team on the ground decides the best route. That works, well, when the people closest to the customer can see constraints and opportunities faster than a central process can. Fintech rarely gives you one clean use case. One customer wants speed inside spend management. Another wants a control review before anything moves, and another only wants suggestions rather than automatic action. A rigid script breaks down when those differences matter. An FD pod can respond quickly because it owns the practical details. Instead of waiting for a larger platform change, it can reshape scope, data access, review steps, and metrics to match the customer's operational reality. That kind of narrowing keeps the assistant inside a safe and useful boundary. Rather than answering anything finance-related, the team limits it to approved policy questions and makes the answer traceable with citations. Retrieval matters because it controls what the model can rely on. If the assistant only searches customer-approved documents, the output stays aligned with their own source of truth instead of drifting into general language model guesses. Any step that touches money or compliance deserves a checkpoint. Human review gives the team a way to catch bad actions before they become real financial or regulatory problems. The metrics should reflect whether the workflow actually helps the business. Faster resolution, fewer errors, lower review load, or better policy adherence matter more than whether the model feels impressive. That is the operating pattern to keep in mind. One shared mission, flexible execution close to the customer, and responsibility for the outcome. In a regulated environment, that balance is what makes local adaptation practical instead of chaotic. Field autonomy only works when teams can make local decisions without pulling the product in random directions. The balance matters because too little freedom creates bottlenecks, and too much freedom creates inconsistent systems. When a team has almost no autonomy, every decision gets pushed upward and the pod stops behaving like a product team. When autonomy goes too far, each group starts solving the same problem in different ways, and the company loses coherence. In a regulated setting, freedom has to sit inside guardrails. A pod can choose how to learn from customers, how to build the feature, and how to stage deployment, but the safety rules, security standards, and architecture boundaries stay fixed. An agent is a system that can take actions toward a goal, not just generate text. Reliability and governance answer three questions: what it may do, what it must never do, and when a human steps in if behavior goes off track. For finance work, the real test is whether the process behaves the same way every time people rely on it. A smart answer is not enough if the surrounding workflow is uncertain or hard to control. Permissions define who can do what, and they stop the system from reaching into actions it should never take. That keeps responsibility tied to the right people and the right roles. Logging creates a record of what happened, which is essential when you need to audit behavior or investigate a mistake. Without that trace, the system becomes hard to trust. Fallbacks decide what happens when the agent cannot proceed safely. A good fallback is boring in the best way. It preserves the workflow instead of forcing a risky guess. Some actions need a human checkpoint before they go live. That review step is what keeps high-impact decisions from being made automatically when the cost of error is too high. If the system starts behaving differently from what was approved, there has to be a fast way to shut it off or revert it. That kind of control is what keeps drift from turning into damage. The organization wants teams close to the work, but it also wants them operating inside consistent controls. That pairing lets the pod move fast without losing safety, accountability, or architectural order. RAMP's reported FD pod model is built around 4 ideas, and the important question is how those ideas turn into daily work. The value of this part is in seeing the principles as an operating system for the team, not just a list of values. The source material here does not let us quote RAMP directly. So the careful move is to treat the principles as a reconstruction rather than a verbatim company statement. That matters because good analysis separates what is documented from what is inferred. Taken together, these 4 ideas describe a tight feedback loop. The team stays near customer problems, ships quickly, owns the path into production, and then uses what it learns to improve the product itself. Those ideas are familiar on their own, but structure is what gives them teeth. A pod turns a general intention into a workflow with ownership, speed, and accountability built in. This contrast gets at the core of the model. Principles tell people what good looks like, while the operating model decides whether the organization can actually behave that way under pressure. That test separates a custom service from a durable system. If the customer can only succeed while the pod is present, the team has created dependence. If the deployment still stands on its own, the pod has created something reusable. A realistic field vignette shows how the technical pieces meet a real business problem. The point here is to see what an FD actually has to shape when the stakes are accuracy, trust, and workflow adoption. A finance operations team usually wants speed without losing control. They need an assistant that can answer policy questions and sort expenses in a way that matches how finance already works. The messy part starts when the assistant has to work across separate systems and imperfect documents. A polished demo can hide risk, but finance cares about wrong interpretations, uneven answers, and people trusting the system more than they should. An FD pod does not try to fix everything at once. It narrows the scope, puts guardrails around the data, and then builds the checks needed for real use. Start with one workflow that matters and can actually be judged. A smaller target makes it easier to see whether the assistant helps or just looks impressive. Limit the assistant to sources the finance team trusts. That reduces bad retrieval, keeps the system aligned with policy, and makes audits much easier. When a model is unsure, a person should make the call. That keeps edge cases from turning into silent errors and gives the team a safer operating model. Evaluation has to cover both helpful answers and safe refusal. A good system knows when to answer, when to defer, and when not to guess. Rollout should be judged by behavior, not excitement. If people use it, resolve questions with it, and rely on it less often for manual work, then the rollout is actually working. The production signal is concrete. Usage counts, escalation rates, reviewer load, and the amount of manual searching the team still has to do. Those measures show whether the assistant is helping the process or just sitting there. That is the FD's real job in a fintech scale-up. Take a promising model and shape it into something the business can run, measure, and trust. LLM application architecture is about how the pieces around a language model fit together, not just the model itself. The important part is understanding the whole system well enough to see where requests enter, where data comes from, and where control is enforced. LLM means large language model, and application architecture means the arrangement of components in a working system. That distinction matters because people often talk about the model as if it were the whole product, when in practice it is only one piece of a larger setup. A deployed system is usually built from several layers, each with its own job. Listing them separately makes it easier to see why an FD needs to think beyond prompts and model quality. The user interface is where the person actually interacts with the system. It shapes the experience, but it also sets expectations about what the system can and cannot do. The model itself does the language processing, prediction, and generation. Its strengths and limits define the raw capability the rest of the architecture has to work with. Data sources matter because the model usually needs more than its built-in memory. A good architecture decides what information can be pulled in and under what conditions. The retrieval or orchestration layer decides where a request should go and which tools or documents should be involved. That layer often turns a generic model into a system that can answer with the right context. Safety and permission checks control who can do what and which actions are allowed at all. In real products, those guardrails are often just as important as the model output itself. Monitoring tells you whether the system is behaving the way you intended. Without that visibility, failures can hide behind a fluent answer and only show up after users are affected. An FDE works across the boundary between customer needs and system design. That means understanding the workflow well enough to choose a sensible architecture and understanding the architecture well enough to explain its limits honestly. Fintech adds stricter requirements around who can see what gets recorded, and what happens when the system cannot complete a task safely. Those details may feel unglamorous, but they separate a convincing demo from something that can survive real use. Customer problem discovery is the part that actually drives the pod model. The code can be good, but the harder skill is finding the right problem because that determines whether the work is useful or just technically polished. That shift matters because coding starts after the problem is understood. If the team can frame the customer's real pain clearly, the solution becomes much easier to design and much more likely to fit the business. A better discovery question looks at the workflow, not just the feature request. You want to know what job the person is trying to finish, where the process gets stuck, and what the cost would be if the model makes the wrong call. In fintech, those questions quickly expose the real constraints around the system. Once you understand the users, the approvals, the data, and the error costs, the architecture starts to make sense. The user is not always the same person who benefits from the result. In financial workflows, the person doing the task, the person reviewing it, and the person accountable for it can all be different. Approval tells you where human judgment still has to stay in the loop. If a manager, analyst, or compliance team has to sign off, the system needs to support review instead of pretending the model can act alone. Data access shapes what the model can safely do. A system with only public information needs a different design from one that can read account history, internal notes, or transaction records. Error cost is one of the biggest design inputs. A false positive and a false negative can have very different business consequences, so the tolerance for mistakes has to be explicit. That question points straight to the best place to automate first. If a team spends hours on repetitive review, routing, or extraction, even a partial AI assist can remove a lot of friction. Those answers let the pod choose the right pattern instead of forcing one generic AI approach. Sometimes the job is retrieval, sometimes classification or summarization, and sometimes the right answer is a workflow where the model helps a person rather than replacing them. That same discovery process teaches the company how to generalize. One customer's request often contains a reusable pattern, and the FD role is to translate that pattern into a product decision the rest of the business can invest in. FD involvement changes the problem from a vague opportunity into a working deployment path. The useful question is not whether the model can do the task, but whether the customer can use it safely and repeatedly. A before and after comparison makes the value much easier to judge. It shows whether the team has moved from a promising idea to something that actually fits the customer's workflow. Before that involvement, the need sounds interesting but still sits in the danger zone. The product team can sense demand, yet the use case is too loose to generalize and the workflow can break in practice. Once the work lands on the right shape, the outcome should be visible in three places: the use case, the adoption signal, and the product signal. Each one tells you something different about whether the solution is becoming real. The first shift is scope. The problem gets narrow enough to implement, and there's a clear path from prototype to deployment instead of an open-ended pilot. The second shift is evidence. Real usage and finished workflows tell you that people are not just trying the tool, they're actually completing work with it. The third shift is direction. The product team can now tell which behavior, workflow, or capability deserves to become part of the standard product. That feedback loop is the real asset. The pod is not only delivering value to the customer, it is also producing evidence that helps the company decide what to turn into the next standard capability. This part shifts from the company's story to the candidate's signal. The point is what kind of experience a fintech scale-up actually values, and how to talk about it in a way that sounds real to a hiring manager. A fintech scale-up is not hiring for vague enthusiasm about AI. It wants people who can look at a messy financial workflow, understand the real constraints, and shape something safe enough to run in production. That changes what counts as a strong interview story. The best candidates can walk through the problem, the change they made, the evidence that people used it, and the learning that came back from the field. Start with discovery. A good candidate can show how the customer pain was found, not guessed, through conversations, observation, or repeated failure in the existing process. Then comes the intervention itself. The important detail is the workflow change because that shows the candidate can move from an idea to an operational improvement. Adoption needs a signal in production, not just a demo. A real metric shows whether people actually use the system and whether it affected the work. The final piece is feedback from the field. That learning shows the candidate can listen to usage, adapt the product, and carry those insights into the next version. That makes for a stronger interview narrative than a polished prototype alone. In a pod model, the prototype only matters if it creates adoption, learning, or a clear path to the next step. The practical test is whether a risky manual process becomes something controlled, measurable, and reusable. That is the operational story a fintech FD should be able to tell, and it sets up the broader question of how a large enterprise turns that same pattern into a customer-facing product motion. Salesforce turns the field-deployed engineer relationship into a repeatable offering, and that shift matters because it moves FD work from ad hoc support into something the company can manage, explain, and scale. The useful lens here is conversion. A role that used to sit close to engineering gets translated for account teams and product leaders. Once that happens, the work becomes easier to route, easier to sell, and easier to connect to customer outcomes. Enterprise software lives inside large organizations, so adoption depends on procurement, security, process change, and multiple people making a decision together. Real AI deployment has the same shape. It has to fit a workflow, survive constraints, and show measurable use, not just impress in a demo. Momentum shows the operating model very clearly. Because requests go through account executives, the FD motion stays tied to account strategy rather than becoming a loose, inbound support queue, and that keeps the work aligned with revenue ownership. A free program usually serves two jobs at once. It helps customers start. It teaches the company where value is concentrated. When a paid version appears, the relationship is no longer just a support function. It is becoming a productized service with a clearer business model. The shift is from a vague AI wish to a deployable customer problem. The important change is not the model first. It is the clarity around workflow, constraints, and what success has to look like. A customer can have a real business goal and still lack the detail needed to build safely. When the workflow and data dependencies are fuzzy, a demo may look strong while remaining too fragile to put into use. That life cycle gives each stage a different job. Early on, the question is whether the problem is worth solving. Later, it becomes whether the solution survives real constraints and can be maintained without constant rescue. In a Salesforce setting, the FD turns a promising idea into a bounded use case. The company sets the goal and limits, while the FD uses field judgment to adapt the approach and bring back what was learned. The job is to look past the request and find the bottleneck underneath it. A complaint about speed might actually be a routing problem, a classification problem, or a missing approval step. So the first task is to isolate where the workflow really breaks. A concrete example makes the difference easier to see. A small scenario will show how a polished prototype can still run into deployment issues the moment it meets daily work. A summary tool can look excellent in a controlled demo and still struggle once it meets real team behavior. The friction usually comes from messy input, privacy review, and unclear ownership of the final result. That kind of friction changes the shape of the solution. The FD narrows the task, defines acceptable inputs, adds a human review step, and chooses the smallest safe piece to automate first. The real divide is between something that can be shown and something that becomes part of routine work. Time to first value matters because one useful workflow builds trust faster than trying to solve everything at once. Each engagement sends back product learning, common workflows, required integrations, adoption blockers, and features that need hardening. That feedback loop turns field work into a guide for what should be built next. The focus here is how Salesforce turns FD talent into a repeatable internal system. The point is not just hiring people who can do the job, but training them so the company can reliably produce that skill again and again. That matters because a services model becomes durable when the organization can scale the people behind it. If the training path is weak, the service stays dependent on a few specialists instead of becoming a capability the company can grow. That sequence shows a clear learning ladder. First the product, then real customer situations, then a project that forces judgment, and finally a high-contact phase where the lessons get sharpened. The important idea is that FD skill comes from practice under constraints, not from passive instruction alone. That transition is the heart of the curriculum. Knowledge starts abstract, then gets tested against actual customers and actual workflows until it becomes usable judgment. Each stage adds a different kind of pressure. Technical training builds credibility. Field work builds discovery skills. The capstone turns learning into an outcome, and the on-site intensive compresses feedback, so the trainee learns how to hand off work cleanly. Being near the customer does not automatically create organizational knowledge. The company has to capture what happened, turn it into a pattern, and carry it into the next engagement. Otherwise, the same work gets redone from scratch every time. That is why handoff matters so much. A good FD leaves behind a solution that other teams can support, a customer who can actually use it, and clear notes on assumptions and ownership, so the work does not depend on one person's memory. That question is a simple test for productization. If the answer is fuzzy, then the engagement produced activity, but not reusable knowledge. If the answer is clear, the field work is feeding the organization instead of disappearing into one-off effort. Salesforce sits between several business models, and that mix changes how the FD role works. The rest of this section shows why the program feels more like a productized operating system than a loose collection of custom assignments. A startup usually uses FDs to handle uncertainty and move quickly. A lab uses them to probe what customers will accept, while a services firm uses them to deliver custom work for a fee. Salesforce is closer to a product company, but it still needs high-touch deployment to make the product work well in real accounts. Those choices change both the economics and the org design. Nomination only keeps the motion strategic, and Ready in 6 turns onboarding into a standard process instead of a personal favor from one strong mentor. The result is a more structured customer experience and an internal model that can be taught and repeated. That is why these roles now sit across product, engineering, and account strategy. Strong candidates need both technical judgment and customer empathy, because the job is not just to test a model or just to calm a client. It is to follow a deployment from first problem discovery through lifecycle thinking and into a handoff that actually holds up in practice. That origin story captures the shift clearly. A narrow expert function becomes a structured customer-facing program that can be nominated, trained, delivered, and eventually tied to revenue. In enterprise settings, that is what productizing the FD relationship really looks like. The same pattern changes again when the buyer cares less about broad software adoption and more about operational trust. Reliability and permissioning becomes central because the customer cannot afford loose edges in a mission-driven environment. The next step is to see how the program adapts when trust is not a nice-to-have, but the main requirement. The same FD role can look even sharper in defense-adjacent settings, where the job is to connect fast-moving model teams to institutions that cannot afford improvisation. The important shift is organizational, not just technical. In these environments, the FD sits between the people building the system and the people who need it to behave reliably under pressure. So translation and trust matter as much as the model itself. That distinction matters because the evidence is mixed on purpose. Public materials can show the role shape, while a field vignette can show how the work feels when constraints are real. Keeping those apart avoids turning inference into hype. The clean split is simple. One side comes from company-authored material, and the other is a constructed example meant to illustrate the operating pattern. That lets us talk about the role honestly without pretending every detail is verified inside one specific company. The buyer profile explains why the role exists at all. When a customer works in public safety, defense, or critical infrastructure, the FD has to turn a messy field problem into a system design, then stay close enough to make sure the deployment holds up under real conditions. That is why a company like Anduril is a useful example of this culture. The economics have to support long build cycles and deep integration work, because the product only matters if it survives contact with a mission user and the constraints that come with that environment. Defense and government-adjacent work changes the sales motion because the environment is harder, the risks are higher, and the users judge the system by whether it behaves reliably under pressure. A normal enterprise pilot can survive a little mess if the value is obvious. In this setting, the system may face segmented permissions, sensitive data, and limited internet access, so the first concern is whether it still works in the real operating conditions. Once the environment gets tighter, the field engineer stops being just a helper during deployment. The role expands because the problem, the boundary, and the proof all become more demanding. First, the question becomes operational. Which decision, alert, or handoff actually improves if the system exists? Second, the deployment boundary is narrow, so access rules and network limits shape the design from the start. Third, success means adoption in real conditions, with fewer workarounds and fewer failures than the current process. That is why the role reaches beyond support. The engineer has to translate user needs into product shape, fit the system into the environment, work alongside the customer in the field, and keep reliability in view the whole time. Public materials show the role as a real operating pattern, not just a title on paper. The useful question is how these companies describe the work when they talk about it themselves. That caveat matters because the evidence here comes from company-written material, not from a single insider account. It gives us a careful snapshot of how the role is presented publicly, which is still enough to reveal the shape of the job. Across Palantir, OpenAI, and Salesforce, the same idea shows up again and again. The engineer works close to customers, close to deployment, and close to the messy details of the environment. That means the job is not just building a model or writing generic software. It is adapting technical work until it fits the real workflow the customer actually has. That phrasing captures the practical side of the role. The engineer learns from the field, watches how people really work, and adjusts the system from that feedback instead of relying on a requirements document alone. This vignette shows how an FD works under real constraints. Messy inputs, human review, and a workflow that has to earn trust before it can change daily operations. The example is intentionally reconstructed from common patterns, so the focus stays on the job and the workflow rather than on one customer's private details. That matters because the lesson is about how the role behaves when the environment is imperfect and the stakes are real. A team like this often starts with disconnected tools and a generic assistant that looks helpful until the context gets complicated. The real cost is not just speed. It is the time spent reformatting, verifying, and fixing mistakes when the system chooses the wrong source or misses an important detail. The first move is to study the problem before touching the model. An FD looks for the bottlenecks, the failure points, the data that can legally and safely enter the system, and the decisions that must stay with a human. From that discovery work, the architecture becomes more specific. Approved documents may need retrieval. Incident details may need a structured form. Triage may need a classifier, and final actions may need a human checkpoint. The model becomes one part of a larger system instead of a standalone answer engine. That division of labor is the core design problem in sensitive settings. The system has to say what the model may propose, what it must hand off, what gets logged for audit, and what a person must confirm before anything moves forward. Deployment only matters when it is measured against real tasks. The team tests whether the system retrieves the right records, flags the right incidents, keeps the required format, and fails safely when confidence is low, because a convincing answer is not enough if it creates risk. Production adoption shows up when people keep using the workflow after the excitement fades. At that point, feedback from operators can be traced back into improvements, and the product has become part of how the team actually works. The FD role changes a project from a vague idea into a deployed system with ownership, safety, and feedback loops. The contrast between before and after shows why this role matters in real customer work. A good way to understand the role is to compare the state of a deployment before the FD arrives and after the work is fully shaped. The difference is not just better code. It is clearer scope, cleaner workflow, and a system that can survive real use. Each row shows the same shift from ambiguity to operational control. The problem gets narrowed, the system gets designed around a mission, the human role becomes explicit, and reliability moves from demo confidence to measured checks. Governance and product learning change too, because production use creates logs, reviews, and evidence that can shape the next version of the product. That pattern is the center of the role. The FD is expected to turn a customer mission into something that can run in production and then carry the field evidence back into the product team, so the system improves instead of staying frozen as a one-off deployment. Patient capital buys time for the slow, unglamorous work that makes deployment stick. It lets a company handle permissions, training, boundary setting, integration, and all the follow-up that turns a pilot into something durable. The important part is that these tasks do not look exciting on a spreadsheet, but they decide whether customers actually keep using the product. A team with patient capital can keep investing in that work long enough for adoption to become real instead of fragile. Field autonomy fits that same logic. The engineer closest to the customer needs enough context and authority to make a good call on the spot, because waiting for every decision to climb a long internal chain slows everything down. In a mission setting, that speed and judgment matter more, because the environment changes fast and mistakes are harder to absorb. This part connects the model's behavior to the kinds of organizations and people it serves best. The defense-adjacent case makes those preferences much clearer. That earlier question about who benefits from the model gets more precise here. When the work is tied to defense or other mission-critical settings, the pattern of support, process, and customer needs becomes easier to see. The common thread is not just industry, but operating environment. Some teams are much better fit because their work demands coordination, patience, and close feedback rather than fast, generic delivery. A team needs a reason for the system to exist beyond novelty. When the mission is concrete, the engineering choices stay anchored to real outcomes instead of drifting toward features that look useful but do not matter. These deployments often take time, and that changes who can participate. If the organization cannot support a longer rollout, the work stalls before the system has time to mature in the field. Some users need the system adapted to their environment, their rules, and their workflow. That kind of customer values precision and fit more than a one-size-fits-all product. The system improves when real users can push on it and report what breaks, what confuses them, and what still needs to change. That feedback loop is expensive, but it is how the product becomes dependable. Early on, the distance between builders and users has to stay small. Putting engineers near the people using the system helps catch mistakes quickly and keeps the product aligned with actual mission needs. The engineers who fit best can work in uncertainty without becoming loose about goals. They know what can be promised, what still needs proof, and where human judgment must stay in the loop. That discipline makes the system safer, easier to use, and easier to trust. That boundary is the real reason the role emerged. The company needed someone who could keep engineering honest about what the system can do and keep the mission side honest about what the system actually needs. Public sector work adds constraints that change both the implementation and the role around it. The important question becomes not just whether the model works, but whether it can survive procurement, security, and operational limits. Procurement can delay decisions long before a pilot starts, and security review can shape the architecture from the beginning. Data handling rules, restricted connectivity, and controlled runtime environments mean the system often has to fit the institution first, not the other way around. That changes the success metric quite a bit. A deployment can be worthwhile even when it reaches only a small workflow at first, if it saves review time, improves consistency, and earns trust inside the organization. Expansion comes after evidence, not before it. Hiring managers in this space are looking for more than technical skill alone. The real test is whether someone can connect customer reality, system design, communication, and reliability into one working practice. The useful pattern is that strong candidates can hold several demands at the same time. They need to understand the operating environment, design within constraints, speak clearly to different audiences, and keep the system dependable under real use. That starts with context, what the customer does, where the work happens, and what pressures shape decisions. Without that, even a clever solution can miss the actual problem. Good design is never abstract here. The solution has to fit security rules, deployment limits, workflows, and the realities of the site, not just look elegant on paper. The work also depends on translation. A strong FD can explain trade-offs, risks, and expectations in language that helps managers and operators make decisions confidently. Reliability matters because pilot success is not the same as field success. If the system cannot survive routine stress, the work never becomes trusted capability. That is why experimentation skill and customer-facing skill each cover only part of the job. The harder judgment call is recognizing when a request sounds technical but actually points to policy, process, or governance. In mission-driven settings, that role keeps AI tied to operations, security, and trust. The goal is not theater. It is turning everyday friction into something that can actually be deployed and used. Once the domain becomes more regulated, the same pattern gets renamed and tightened. The next shift is about how those responsibilities change when law, compliance, and professional standard become part of the design space. Legal engineering shows how a general product pattern gets reshaped for a profession with stricter workflows and heavier risk. The point here is not the name change alone, but the way the role has to respect legal review, privilege, and how attorneys already work. Careful reporting matters because stories about product roles often get exaggerated. In legal, the real constraints are easy to miss unless you look at how teams actually operate, who approves work, and what kinds of mistakes are unacceptable. The job does not disappear. It gets translated into the language of the field. A legal engineer takes messy legal tasks and turns them into something attorneys can deploy, use, and trust inside their own process. That vocabulary shift tells you what the company is worried about. In a general enterprise setting, the challenge is getting software into a workflow. In legal, the challenge is fitting the tool around privilege, review standards, matter context, and the document process without breaking any of them. Legal engineering often starts with a familiar pattern. A promising product runs into the reality of messy legal work. The point of this part is to show why that happens and why the people who bridge product, technical implementation, and customer judgment become so important. A legal product usually begins with a clean idea, but legal work is never clean for long. Contract review, clause negotiation, redlining, and approval routing all contain exceptions, so the system has to adapt to how the work actually happens rather than how it looks on paper. Once those exceptions appear, the work shifts from invention to translation. Someone has to turn a rough product idea into something that fits the legal process and can survive daily use. The first step is to observe the workflow in practice, not in a polished presentation. Legal teams often have informal paths, workarounds, and hidden approvals that matter just as much as the official process. After that, the customer's pain points have to become concrete product requirements. That means deciding what the system must do, what it can safely ignore, and where human review still needs to stay in place. The architecture matters because legal settings have their own constraints around accuracy, traceability, access, and risk. A good design reflects those constraints instead of forcing a generic AI pattern onto the problem. The last part is staying close enough to the live system to measure what it does and correct it when reality changes. In legal tech, trust comes from that feedback loop, not from a one-time launch. That operating style is exactly what people mean when they describe an FD-like role. The label may change from company to company, but the job still combines product sense, technical execution, and the judgment needed to work with customers directly. A strong interview often gets past the job title and gets to the reason the team was created at all. When someone like James Hansa can explain that origin, the company structure starts to reveal its real priorities, and that tells you more than a generic role description ever could. Legal AI usually failed because the problem was broader than model quality. The missing piece was the surrounding system: context, tools, and workflow. The core issue is rarely that AI does not exist. The real gap tends to show up in three places: understanding the work, connecting to the team's systems, and fitting the actual process. A contract tool can sound confident while still missing the matter type, the playbook, the risk tolerance, or the stage of the deal. Those details decide whether a suggestion is safe to use, so text alone is not enough. If the system cannot reach the document repository, the approval flow, or the review interface, it never becomes part of daily work. It may look useful on a slide, but it does not behave like an assistant inside the team's process. Legal teams often rely on unwritten rules that experienced attorneys follow automatically. When those rules are not captured by someone close to the customer, the software misses them and the pilot collapses. That is why legal engineering starts to resemble forward-deployed work. The job is not only to sell software, but to translate how the profession actually works into something the system can support. Contract review is a clear example of how vertical AI gets embedded into real work. The point is to see the workflow, the handoff points, and where human judgment still stays in control. A contract copilot shows the adaptation in practice because the model is not acting alone. It is sitting inside a legal process with specific tasks and constraints. The useful way to think about it is as a sequence of steps where the system gathers context, drafts suggestions, and then routes the result to the right person. The model first helps identify the document and gather matter context. Then it proposes clause-level edits. After that, it highlights risky language and hands the final decision to a lawyer before the document is stored in the firm's system. That division of labor matters more than whether the model can produce polished wording. The system is strongest when it does pattern recognition and first-pass drafting, while the lawyer stays responsible for the legal decision. Legal work adds constraints that shape the design. Sensitive context may need to stay hidden, auditability has to be preserved, and the output has to fit the existing document process. A good workflow respects privilege, controls what the model sees, and keeps a clear record of what changed. That is where legal engineering comes in. It connects the model, the workflow rules, and the firm's systems so the AI output can actually move through a real organization. The real test is whether the work changes once the embedded function joins the process. That shift tells you if the model is just an external idea or something that is actually shaping decisions, workflow, and delivery. A simple comparison makes the idea concrete. Before and after reveals whether the organization is still guessing or whether the embedded team has changed how the product is defined and used. Each row shows a different kind of maturity. The problem becomes specific, the workflow becomes repeatable, the context gets richer, and deployment moves into the tools people already trust. Once measurement and product learning improve too, you know the function is changing the system rather than decorating it. That is the useful distinction. An impressive demo can attract attention, but an embedded legal engineering function creates something people can depend on because it fits their work, improves their judgment, and earns adoption over time. Mission-type tactics fit legal work when the team needs clear boundaries and local judgment. The point is to narrow the mission, keep the rules tight, and let the people closest to the work adapt without losing control. Legal engineering borrows the military idea at a team level. Success comes from a sharply defined objective and disciplined execution, not from trying to solve every related problem at once. That keeps the work practical and reliable inside a regulated environment. An embedded team might own a specific goal, like speeding up first-pass review for one contract family. It still needs room to adjust when users behave differently than expected, because the real workflow always reveals edge cases the plan did not capture. Large legal deployments rarely work as one big rollout. They succeed in stages, because each stage gives feedback about what is stable, what is risky, and what needs to change before the scope grows. Begin with one use case that is small enough to control and valuable enough to matter. A narrow starting point makes it easier to test assumptions and keep the team aligned. Scope has to be explicit, especially with documents. Once the team knows which classes are included, it can build rules and review paths that match the actual risk profile. Governance matters here. The model can assist, but some decisions stay with a human because the legal and regulatory risk is too high to delegate fully. Success has to be measured from the start. Telemetry tells the team whether the workflow is actually improving instead of just feeling faster to the people building it. Expansion comes after stability, not before it. If the first workflow is dependable, the team can widen the scope with much less chance of breaking the process that already works. That is what makes the role difficult. The embedded practitioner is not just shipping a tool, but also defining what the tool is allowed to touch. In legal engineering, the boundary is part of the work, and good judgment lives right there. Customer problem discovery in legal work starts with the real workflow, not with the model. The goal is to find where time, risk, and coordination problems actually live before anyone talks about features. A useful legal solution begins by understanding the problem the team is trying to solve. Model choice matters later. Early on, the important work is identifying the pain point that actually deserves automation or support. In practice, that means sitting with attorneys, contract managers, or legal ops staff and observing the process closely. The bottleneck is often somewhere unexpected: triage, handoff, or even hesitation about who should own review. That question captures the FD mindset. Instead of asking what the model can do, you ask where the current process is losing time, confidence, or consistency, because those are the failures the team actually feels. That kind of discovery usually leads to a more realistic target than a vague request for a copilot. It also reveals what legal teams value most: clear records, human control, understandable outputs in everyday use, and a clean path to escalate uncertain cases. Legal systems force architecture to do more than generate text. The real question is how the model fits into a workflow that can handle risk, review, and accountability. Once the system touches real contracts or policy work, it has to fit the way people actually operate. Speed matters, but so do controls, approvals, and the consequences of a bad change. A legal setup often combines generation with retrieval, so the model can pull the right playbooks or clause libraries before it answers. Then the workflow can route low-risk edits automatically while sending sensitive changes to an attorney for review. That is why the model alone is not the product. Permissions, context handling, logging, human approval, and system integration are part of the actual application, and in legal work they often matter more than the model output itself. Seen this way, legal engineering looks less like branding and more like system design. The core skill is building software that can support legal judgment without breaking the rules around it. Reliability and governance sit at the center of legal AI because the system has to be trustworthy in real use, not just impressive in a demo. The real question is whether the workflow can stand up to review, audit, and professional responsibility. For legal work, those concerns are not extras added at the end. They define whether the tool belongs in production at all, because the deployment has to support judgment, control, and accountability from start. A system can look polished in a short demo and still fail when real cases, real users, and real pressure show up. Attorneys need limits they can understand and behavior they can audit, not just outputs that sound convincing. That is why much of the effort goes into controls that are easy to overlook from the outside. The visible model output matters, but the surrounding process is what turns a promising prototype into something a legal team can actually use. Uncertain cases need a clear path instead of a guessed answer. A strong system knows when confidence is too low and stops short of pretending it knows more than it does. Some outputs should go straight to a person for review, and some should be labeled so the user knows how to treat them. Routing and labeling keep the human decision maker in the loop where it matters. A legal workflow also needs a reliable trail of actions, inputs, and decisions. Those records make later review possible and give the organization evidence of how the system behaved. Access control cannot be vague in this setting. The system has to respect who may see, edit, approve, or export material, because permissions are part of legal governance. When something falls outside the normal path, it needs a defined escalation route. That keeps unusual cases from disappearing into the system or being handled by guesswork. This is where engineering and governance meet. The workflow itself is built to carry the safety checks, review steps, and controls that make the outcome dependable instead of leaving those responsibilities to chance. This checklist turns a broad idea into something a team can actually use. It matters because legal work only works in production when the scope, approvals, and handoffs are explicit. A checklist helps teams ask the same questions every time instead of relying on memory or informal agreement. That consistency is what keeps the workflow safe and reusable. Start by naming the task narrowly. If the scope is fuzzy, the system will drift into work it should not touch, and the review process becomes harder to control. The next question is about inputs. Legal systems often fail at the boundary between allowed and disallowed context, so the team needs a clear rule for what can enter the workflow. That line between suggestion and approval is the governance boundary. The model can draft or recommend, but a person needs to own the decision whenever risk or judgment matters. A useful workflow ends in the right destination, not just in a good draft. If the final document lands in the wrong system, the work may be lost, duplicated, or impossible to audit. Adoption needs a metric, or the team cannot tell whether the workflow is helping. Measures like volume, cycle time, or completion rate show whether people are actually using it. Every deployment needs an escalation path. When a model is uncertain, the data is sensitive, or the output looks legally risky, the issue should move to a human reviewer immediately. That question turns one deployment into organizational learning. The point is not only to solve the immediate legal task, but to feed real constraints back into product decisions. That is the deeper value of embedding legal expertise inside the product process. The company keeps the lesson, not just the feature, and the next workflow start from a better design. The hiring signal matters because it shows the FD pattern moving into regulated industries, not just broad enterprise AI. The label may change from company to company, but the core need stays the same. Someone has to translate messy domain work into something that actually ships. A role like legal engineering tells you the workflow is becoming specialized enough to need domain-aware builders. The title may sit under product, solutions, or applied engineering, but the underlying job is still to turn friction in a real process into a deployed system. That is why the legal version matters even outside legal work. Once a vertical develops its own norms, the FD idea gets renamed, but the demand for people who can bridge domain complexity and software stays recognizable. The useful rule here is to follow the workflow, not just the label on the roll. When an industry changes, the job changes with it, and that is what makes embedded work so different from generic product sale. Legal work is not only a different subject matter, it runs under different constraints. A contract path, an approval process, and a level of risk all shift together. So the model has to adapt to the real operating environment. That origin story matters because it explains the shape of the role. An FD takes a broad product and makes it fit a specific domain by translating expert practice into something the system can actually use. That is the pressure point for the next part of the story. A pitch can look clean in theory, but the real test is whether the system works once it meets messy implementation, live users, and actual constraints. An FD role only makes sense if it can withstand the cases where the work did not hold up. The point here is to test the role against reality, not against the best possible story. A reporting chapter earns trust when it can handle the messy parts, because that is where the model gets tested. If the weak spots are missing, the argument stays polished but thin. A team can be embedded with real intent, real effort, and still end up producing little that lasts. That matters here because the role is only convincing if we also see its limits, not just its promise. The responsible move is to label the gap honestly instead of filling it with a made-up cautionary tale. Until the reporting is verified, the section has to stay provisional. The next question is what this role is meant to solve in the first place. If we do not understand the intended fix, it becomes impossible to judge why the role sometimes falls short. The origin story is straightforward. A company has a strong product, but the customer's problem is too specific for a standard sales motion. Embedding technical people close to the customer helps translate a messy workflow into something the system can actually handle. The role works best when it is treated as a focused field tactic, not as a universal fix. It depends on clear goals, real constraints, and enough authority to change both the software and the process around it. Palantir's public framing gives a useful anchor for that same pattern. Stay close to the customer, work on live operational problems, and turn field knowledge back into product. That supports the origin story, even while a separate failure example still needs solid evidence. When those conditions are missing, the team starts covering symptoms instead of fixing the system. The work may look active, but it is no longer building durable capability. A real failure case has to prove more than disappointment. It needs a traceable chain from the original problem to the deployed work, and then to the reason the effort did not hold up. To count as evidence, the case has to be specific enough to support a conclusion. That means we need the problem, the intervention, the measurement, the learning, and the reason the effort failed or was cut back. First, we need the baseline. Without a clear view of what was broken before the team showed up, there is no way to tell whether the later work changed anything meaningful. Then we need the intervention itself. The reader has to know whether the team made a real product change, a workflow change, or just a temporary patch. Adoption has to be measured in the real environment, not in a demo. Usage, retention, and daily reliance tell a much clearer story than enthusiasm in a pilot meeting. The key test is whether the field work improved the core product. If the learning stayed trapped inside the customer engagement, the organization did not really get smarter. And finally, the ending matters. A real failure case explains why the effort could not justify its cost, its complexity, or its place in the organization. Without that sequence, the account may sound convincing, but it does not prove much. Evidence comes from connected steps, not from a mood of authenticity. While the reporting is still incomplete, the useful move is to describe the pattern rather than pretend to have a finished case. That keeps the lesson grounded without inventing a story. A postmortem usually strips away the marketing language and shows the same basic sequence underneath. That sequence is what matters here, because it explains how a promising embedded team can still miss the mark. The pattern often starts with imitation. Leadership sees embedded AI teams elsewhere and decides to copy the form. The team gathers use cases and produces polished output, but the real workflow never changes enough for the tool to stick. The failure usually comes from several missing pieces, not from one dramatic mistake. Each gap makes the next one more likely. Customer pain is real, but pain by itself is not enough. Good discovery turns vague complaints into a narrow, testable use case with a clear task, user, environment, metric, and tolerance for failure. The system also has to be ready for real conditions. That means data access, retrieval, permissions, logging, human review, and fallback paths. All of the pieces that make a product dependable beyond the demo. Workflow design is where many deployments stall. If nobody has a clear role for review, override, and accountability, the users will try the system once and then retreat to manual work. Anecdotes are not enough to prove production value. The team needs a repeatable evaluation that shows whether the system actually saves time, improves accuracy, or reduces rework. Once the software can act, reliability becomes central. Permissioning, audit trails, escalation rules, and guardrails are what keep an impressive field prototype from becoming an unacceptable production risk. That pattern becomes clearer when it is reduced to a simple story. The details change from company to company, but the failure shape often looks familiar. A postmortem usually turns the abstract pattern into concrete events. The point is to see where the team stopped solving the operational problem and started only showing a successful demo. The starting point is a workflow that already hurts. People are doing repetitive work, moving information through too many handoffs, and losing context as it crosses systems. The pilot may look excellent in a controlled setting because it is built around the easiest path. But a demo path is not the same as a production path, and that difference is where many projects fail. Adoption then exposes the weakness. If active use flattens out or people quietly route around the tool, the company learns that the pilot never became part of daily work. The last failure is organizational. The team may learn something useful, but if that knowledge does not reshape the core product, the field effort remains isolated and fragile. That sequence is what separates a real deployment from a flashy experiment. It shows whether the work changed the organization or only produced a convincing performance. A comparison between the hope for change and the actual result makes the gap easy to see. The important part is not just what was supposed to improve, but why the improvement never fully showed up. The cleanest comparison is between the intended workflow and the one that really happened. That makes the failure legible instead of vague. The table compresses the whole failure pattern into a before and after view. Each stage can fail in a different way, but the same theme appears. The organization gets activity without durable change. That is the hidden downside. The company can look busy, win praise for the pilot, and still fail to build a product organization that is actually better equipped than before. Field autonomy is one of the main reasons the role can work at all, but it also creates the main risk. The same freedom that helps the team adapt can also pull it away from product discipline. The best teams can make decisions quickly while still staying connected to the broader product mission. That balance is hard to maintain, especially when the customer needs immediate answers. If the team is constrained too tightly, it cannot adapt to the customer's reality. If it is left too loose, every project becomes custom work, and the company starts mistaking service excellence for product maturity. A healthy model keeps the team embedded while still making it answer to a shared product direction. If the organization cannot absorb the learning, even a very capable team may end up being temporary by default. A chapter like this becomes more useful when it turns into a checklist you can apply. That way, the idea is not just descriptive. It becomes something you can test against real teams and real deployments. Before calling an initiative a success, the simplest move is to interrogate the evidence. These questions reveal whether the team really built a function or only ran a promising pilot. Each question targets one failure mode we have already seen. If the answers are vague, the company may have activity and talent, but not the structure needed for durable outcomes. That distinction matters a lot. A company can hire capable people and still fail to create the systems, metrics, and feedback loops that make the role effective. The hiring market will keep rewarding people who can work in ambiguity, but titles alone do not prove that the function is healthy. The same label can signal real ambition in one company and unresolved organizational confusion in another. As more companies adopt embedded AI roles, the titles will keep changing, but the basic test stays the same. The real question is whether the role produces reusable value or just reflects an unresolved boundary between product and services. Candidates should ask about the outcome, not just the org chart. A pilot only matters if it leads to something durable afterward. The lasting rule is simple. Proximity to customers is not enough on its own. What validates the role is proof that the workflow improved, adoption rose, and the product team learned something reusable. Validation comes from a visible before and after shift. A broken workflow becomes usable, the production path gets stronger, and the organization can reuse what it learned. The most honest version of the argument still needs a verified failure case of its own. A shutdown, retrenchment, or scaled-back team would make the chapter much more credible because it would show where the model stopped holding. From there, the discussion can widen out to the patterns that separate durable embedded work from expensive theater. That broader view is what turns one case into something that can teach us more generally. Cross-case pattern recognition is about comparing different companies until the common operating pattern stands out. The point is not to force them into the same story, but to see which parts repeat and which parts really differ. A reporting chapter becomes useful when you stop treating each company as a one-off story. Put the cases next to each other and the surface details shift while the underlying logic keeps showing up in similar ways. That question matters for an FD, a hiring manager, or a customer deciding whether embedded AI will fit their world. You are looking for the durable pattern, but you also need to see the boundary where a pattern stops being transferable. This part isolates the three conditions that make the role show up across very different companies. Once those conditions are clear, the pattern stops looking accidental and starts looking structural. Across the examples, the same three ingredients keep returning. They're the reason the role can function as something more than a temporary fix. The first ingredient is a long enough time horizon to support work that does not pay back immediately. That patience matters because the team can learn from a customer-specific deployment and feed those lessons back into the product instead of forcing every customer into a rigid standard package on day one. The second ingredient is real decision-making power where the work happens. The embedded engineer has to choose priorities, instrument the system, simplify what is messy, and know when to escalate or push back. Otherwise, the role loses its speed and turns into ordinary support. The third ingredient is a short path from customer problem to product improvement. Field work only becomes strategic when the team can tell the difference between a one-off workaround and a general failure mode, then hand that insight back to the core platform quickly. Those three traits explain why the function appears in such different origin stories. In each case, leadership treats customer pain as product signal, so the role becomes a bridge between immediate delivery and long-term platform design. The important part now is where these roles stop looking the same. Industry, deal size, and regulation push the work in different directions, and those differences change what the engineer actually has to do. A title role can look similar on paper, but the details decide the day-to-day job. Two companies may both hire an FD and still expect very different kinds of work from that person. Industry shapes who is involved in the decision, how fast systems can move, and how much uncertainty people will accept. In one company, a pilot only works if it is tightly controlled. In another, the same pilot might be accepted as an early sketch of the solution. A large account can justify deep customization because the revenue is big and the stakes are high. A product-led motion has to be more selective, so the engineering effort goes into making a smaller set of workflows usable for many customers. Regulated settings add another layer of work beyond the core business problem. The engineer has to think about data handling, model behavior, audit trails, and how changes are approved, while lighter environments shift more of that effort toward workflow design. A useful comparison starts with the job each company needed done, not with the title of the role. That lens shows how the same field team can build very different things depending on whether the customer needs deployment, adoption, product fit, or production trust. The table maps the same role across four settings. An important pattern is the kind of friction being removed. In one case, the work is about wiring systems together. In another, it is about making model behavior dependable. Elsewhere, it is about turning a vague request into a repeatable implementation or adding controls so production use feels safe enough to continue. That is why the table is useful without pretending the jobs are identical. The center stays on translating customer needs into something usable, but the emphasis shifts from one company type to another, and that shift tells you what product lessons the team is likely feeding back. A real deployment makes the role clear. The job is to turn messy operations into a reliable workflow. That matters because the hard part is usually not the model itself, but getting useful work done inside a live organization. The customer is not shopping for a generic feature. They need something that works across multiple data sources, real users, deadlines, and all the friction that comes with production use. Before a forward-deployed engineer steps in, the process is often fragmented. People patch together whatever tools they have, but the path from raw data to a decision is slow, inconsistent, and hard to trust. The important change is the sequence of work. Someone has to decide which data source counts as authoritative, where a person should review a result, and which parts belong in automation versus human judgment. A successful deployment shows up in the process, not just in the presence of AI. The team gets to a decision with less rework, and the product knowledge becomes reusable. Connectors, default policies, evaluation gates, and hard limits on automation. That is why the role grows out of repeated exposure to real deployments. The recurring lesson is that model quality matters, but the bigger challenge is building a governed system that fits the constraints of the workplace. The center of technical work is shifting towards systems where models, data, tools, and safeguards have to operate together. That matters because the hard part is no longer only building the model. It is making the whole application reliable enough to use. A production LLM system usually has several layers around the model itself. Retrieval, prompt design, tool use, logging, redaction, approval steps, and rollback paths all have to line up, and the FD sits right at that seam where the pieces meet. Evaluation-driven deployment means the release decision comes from evidence, not from a demo that merely feels convincing. You define what success looks like, test real cases, study the failures, and use that data to decide whether the workflow is ready for wider use. Once a system affects customers, employees, or mission work, the questions become operational and governance heavy. Someone needs an answer for overrides, logging, reversibility, and escalation when the system sees a case outside the normal pattern. A useful agent is not just capable of acting, it has to act inside clear limits. It should surface uncertainty and fail in a way the business can absorb, because reliability and governance are really the same problem at release time. The market is rewarding people who can connect product sense, customer reality, and deployment under uncertainty. That combination explains why the title changes from company to company, even when the underlying need looks very similar. A label like customer-facing engineer only tells part of the story. The real demand is for someone who can move between what the product can do, what the customer needs, and what it takes to make it work in the field, especially when the situation is still changing. That makes the candidate profile much narrower than it first appears. Coding skill alone is not enough, and customer communication alone is not enough. The valuable part is turning one broken workflow into a reusable product improvement. For a hiring manager, the test is simple. After the embedded engineer gets involved, the team should be able to point to a real change in the workflow or the product. If that change never appears, the role is probably drifting toward pre-sales, implementation, or support, which are useful jobs but a different model. Embedded functions are judged by the change they create, not by how close they sit to the customer. The useful test is whether the company can do something now that it could not do before. Being near the customer can help, but it is not the definition of the role. The real measure is whether the team expands what the company can understand, deliver, or improve. Those four signs tell you the work had impact. If each customer engagement leaves behind learning the product team can reuse, the function is building something durable instead of spending effort once and discarding it. That is why the role appeared in the first place. Enterprise AI only matters when a broken workflow becomes repeatable, and that shift from one-off service to repeatable process is what turns the function into part of the product engine. The next question is practical. Which signals show that the team has become part of the organization, and which signs show it is still only providing short-term help?